Greetings to one and all. I am 19BQ 180440 GC Raviteja from second year of ECE. I am here to explain some topics of random variables and stochastic process, electromagnetic waves, and analog circuits. First of all, let me start with the topic of noise from random variables and stochastic process. Classification of noise. First of all, noise can be defined as the follows. Noise is a random undesirable electrical energy that enters the communication system via the communicating medium and interferes with the transmitting message. However, some noise is also produced in the receiver. Or it can also be defined as, with reference to an electrical system, noise may be defined as any unwanted form of energy which tends to interfere with the proper reception and reproduction of the unwanted signals, which means it involves with the unwanted signal and disturbs the communication system, entire communication system. Noise may be put into the following two categories. First one, external noise, that is noise whose sources are external. External noise may be classified into three types: atmospheric noise, extraterrestrial noises, man-made noise, or industrial noises. This on the other classification of the noise is internal noise in the communication, that is noises which get generated within the receiver or communication system. Internal noise may be put into the following four categories: thermal noise or white noise or Johnson noise, short noise, transmit time noise, miscellaneous time noise. External noise cannot be reduced except by changing the location of the receiver or the entire system. Internal noise, on the other hand, can be easily evaluated mathematically and can be reduced to great extent by proper design. As already said, because of the fact that the internal noise can be reduced to a great extent, the study of the noise characteristics is very important part of the communication system. First of all, let me explain about the external noise. The atmospheric noise or static noise is caused by lightning discharges in the thunderstorms and other natural electrical disturbances occurring in the atmosphere. These electrical impulses are random in nature. Hence, the energy is spread over the complete frequency spectrum over the radio communications. Atmospheric noise accordingly consists of spurious random signals with components spread over the wide frequency range. The spurious radio waves constituting the noise get propagated over the earth in the same fashion as the desired radio waves for the same frequency. Accordingly, at the given receiving point, the receiving antenna picks up not only the signal but also static form from all the thunderstorms, local or remote. Extraterrestrial noise. In extraterrestrial noise, there is subdivision noise, subdivision classification, solar noise, cosmic noise. Solar noise, this is the electrical noise emanating from the sun. Under quiet conditions, there is a steady radiating of noise from the sun. This results because sun is a large body at a very high temperature exceeding 600 degrees Celsius on the surface and radiates electrical energy in the form of noise over the very wide frequency spectrum, including the spectrum used for radio communications. The intensity produced by the sun varies with the time. In fact, the sun has a repeating linear noise cycle. During the peak of this cycle, the sun produces some amount of noise that causes tremendous radio signal interference, making in many frequencies unusable for communications. During other years, the noise is at a minimum level. Cosmic noise. Distant stars are also suns and have high temperatures. These stars therefore radiate noise in the same way as our sun. The noise received from these distant stars is thermal noise and is distributing almost uniformly over the entire sky. We also receive our noise from the center of our galaxy. Our galaxy name is Milky Way galaxy, from other Milky Way galaxy, from other distant galaxies and from other visual point sources such as quasars and pulsars. These all are extraterrestrial species. Man-made noise, industrial noise. By man-made noise, industrial noise is mean that the electrical noise produced by such systems are automobiles and aircraft ignitions, electrical motors and switchgears, leakage from the high voltage lines, fluorescent lights and the numerous other heavy electrical machines. Such noises are produced by the arc discharge taking place during the operation of these machines. Such man-made noises are most intensive in electrical and densely populated areas. Man-made noise is such areas far exceeds from other sources of noise in frequency range exceeding from about 1 MHz to 600 MHz. The other noise is classification. The other this can be internal noise, which is also a burden to the communications. Next, let me explain power amplifiers. Power amplifiers. Power amplifiers. Power amplifier traffic is a topic from analog circuits. Power amplifier classes. There are multiple ways of designing a power amplifier circuit. The operation and output characteristics of each of the circuit configuration differs from one another. To differentiate the characteristics and behavior of different power amplifier circuits, the power amplifier classes are used in which letter symbol are assigned to identify the method of operation. They are broadly classified into two categories. Power amplifiers designed to apply analog signals come under categories B, AB, or C category. Power amplifier designed to amplify pulse width modulated PWM digital signals come under P, D, E, F, etc. The most commonly used power amplifier are the ones used in audio amplifier circuits, and they come under categories under classes A, B, or C. So let's take a look at them in detail. Class A power amplifiers. Analog waveforms are made up of high positive high and negative lows. In this class of amplifiers, the entire input waveform is used in amplifier process. In single transistor is used to amplify both the positive and negative halves of the waveform. This makes the design simple and make class A amplifier the most commonly used type of power amplifiers. Although this class of power amplifiers are suppressed by the better designs, they are still popular among the hobbyists. This is a circuit of class A amplifier. In this class of amplifier, the active element, the electronic component used for amplifying which transistor in this case is in use all the time, even if there is no input signal. This generates almost of heat and reduces the efficiency of class A amplifiers to 25% in case of normal configuration and 50% in case of transformer coupled configuration. The conduction angle, the portion of the waveform used for amplification out of 360 degrees for class A amplifiers is 360 degrees. So the signal distortion levels are very less, allowing better high frequency performance. Now let us look into the class B power amplifier. The class B power amplifiers are designed to reduce the efficiency and heating problems present in the class A amplifier. This is came after the class A amplifier. Instead of a single transistor to amplify the entire waveform, this class of amplifiers use two complementary transistors. One transistor amplifies the positive half of the waveform, and other amplifies the negative half of the waveform. So each active device conducts for all half of 180 degrees of the waveform, and two of them when combinedly amplified the entire signal. This is a circuit of class B output waveform, which is due to the input waveform. Upper transistor works for positive cycle, the below transistor works for the negative cycle. Efficiency of class B amplifiers is improved a lot over the class B amplifier because of these two transistor design. They can reach the theoretical efficiency of about 75%. Power amplifiers of this class are used in battery operated devices like FM radios or transistor radios. Because the superposition of the two halves of the waveform, there exists a small distortion at the crossover region. To reduce the signal distortion, AB are designed. If we found a problem in class A, we found class B. As there is a problem in class B, we go for class AB. Class AB power amplifier. Class AB power amplifier are a combination of class A and class B amplifiers, which take the advantages of both class A and class B. This class of amplifiers are designed to reduce the less efficiency problem of class A amplifiers and distortion of the signal over the region in class B amplifiers. This is the structure of the class AB. The conduction angle is 180 degrees. below 180 degrees. It contains high frequency response like in A amplifier and good efficiency as in B class B amplifier. A combination of diodes and resistors are used to provide little bias voltage which reduces the distortion of the waveform near the crossover region. There are little drop in efficiency 60% because of this. Class C power amplifier. The design of Class C power amplifiers allows greater efficiency but reduces the linearity conduction angle which is under 90 degrees. In other words, it sacrifices the quality of amplification for increase in efficiency. Lesser conduction angle implies greater distortion, and so this class of amplifiers are not suited for audio amplification. They are used in high frequency oscillators and amplification of radio frequency signals. Class C amplifiers generally contains a tuned load which filters and amplifies input signals of certain frequency, and the waveform of other frequency are suppressed. This is the circuit of Class C. In this type of power amplifier, the active element conducts only when the input is above a certain threshold, which reduces the power dissipation and increases the efficiency. Other power amplifiers classes D, E, F, G, etc. are used to amplify the PWM signal, pulse width modulated signals. They are come under the category of switching modulator amplifiers and turn the output either constantly on or constantly off without any other levels in the between. Now, as the topic of from EMF, let us look into the propagation of waves. The electromagnetic waves such as visible light and electromagnetic waves consist of orthogonal electrical and magnetic field, both orthogonal to the propagation direction of wave. The polarization of the electromagnetic waves is meant to describe the magnitude and the direction of the electric field of the wave. Specifically, the polarization of the radiated wave is defined as the property of a radiated electromagnetic wave describing the time varying direction and relative magnitude of the electric field vector. The trace of the magnitude of the electric field vector are observed in the direction of propagation. Introduction: the polarization of electromagnetic EMF is basic property of EMF, which is widely used to control laser interferometry, photography, and such in sketch of the linear polarization red curves of the EMF as shown in the figure. Based on the Maxwell equations of EMF, the electric field can be split into orthogonal x direction Ex, Ey, and Ey. Ex, Ax bar, Ex cos omega t plus phi x. Ey, Ay bar, Ey cos omega t plus phi. Where Ex is the magnitude of the electromagnetic in x direction, Ey is the magnitude of the electric in x direction. Phi is the phase of the electromagnetic wave in the x direction, E is the phase of the electron field in the y direction, and omega is the frequency of the EMW. The three major polarization states are defined based on the differences in phase magnitude of x direction and y direction EMF. The linear polarization, assume Ey is the mathematical expression for the magnetic equals to 0, which gives the definition of electromagnetic field as Ex equal to Ax, Ex cos omega t plus phi x, Ey equal to 0. The electric magnetic on certain propagation position will oscillate only on the x-axis with the angular frequency of the omega, which is shown in this below. This is the figure. X-axis linear polarization. Thus, the similar polarization of the electromagnetic on only a specific straight direction as defined as the linear polarization. On the other hand, Ey is equal to, which gives the electric field as Ex equal to 0, Ey equal to Ey cos omega t plus phi y in the direction of Ay bar. The electromagnetic field only oscillate in the y-axis with the angular frequency omega, which is shown in the figure. Ey as is a graph between Ey and Ex. Y-axis linear polarization. Generally, with the x direction oscillation, y direction oscillation share the same phase. The linear polarization field pattern can be expressed as Ex equal to Ex cos omega t plus I, Ax bar, Ey equal to Ey cos omega t plus xi. The angle of the linear oscillation towards x-axis is calculated as theta equal to tan inverse, ac means tan inverse of Ey by Ex. The polarization sketch is shown in the figure. Linear polarization. Other classification of polarization is circular polarization. Circular polarization is a special polarization state of the electrical polarization state which satisfies the following conditions. The field must have orthogonal polarized components to and the second one is the two components must have the simple magnitude ex equal to ey. The two components must have the time phase difference of multiple of 90 degrees. Thus the field patterns can be written as ex equal to e naught cos omega t ex bar, e naught cos omega t plus n phi by 2 ay bar is odd number, and polarized pattern can be drawn as a figure 4 and figure 5. The left circular polarization is achieved by the number of n to 4m minus 1, and the right polarization is achieved by the number n equals to 4m plus 1. Elliptical polarization, the last classification from the polarization. The elliptical polarization is the general definition of the EMF polarization state whose field can be expressed and make the simple math transformation of Ex and Ey. Ex equal to Er plus El, Ey equal to Er minus El, where Ex equal to Ax by Ex cos omega t plus pi by 2, Ey equal to Ay, so Ey cos omega t. Thus the electromagnetic pattern can be classified as Ex by Er plus El whole square plus Ey by Er minus El whole square. The above electrical polarization, which can be seen as the superposition of two circular polarization processing different magnitude and direction, and the general electrical polarization pattern is shown in the figure below. General electrical polarization, the major minor axis slope is calculated by the phase difference between x components and y components. Thank you. This is the end of my seminar topic.